everyone. I'm Tim Shaffer. I'm a recent hire in the CORTX Advanced Development Group and also community work. And I'm doing the monthly Meet an Architect talk today about multi-site replication, which is one of the things that our group has been working on. So as just a general outline of the presentation, I'll first introduce some of the general concepts, the key terms we'll be working with, what we're trying to do, some of the challenges and simpler things that we might do that aren't necessarily satisfactory. And I'm assuming, general audience don't want to assume lots of particular knowledge about anything. So I'll be trying to introduce things as much as possible. So if you already know about some of this stuff, I apologize. But I wanted to make sure that this was as self-contained as possible. And then the second part is how we will be working on this in CORTX, the architecture that we chose to tackle this issue, and then looking in a bit more depth at the different components that we use for this. So the S3 server, the FDMI interface, and the multi-site replicator. So a few very basic terms. This is all in the context of S3, which is Amazon's simple storage service. Amazon very well documented this protocol, so there's some other implementations too, like MinIO and CORTX as well. The idea here is you can do simple HTTP get put, have some data, and then put it up in the cloud. That gives you an object, which is similar to a file on your computer, basically a name and some data. There's also some metadata, ACLs, other stuff that we don't have to go into. Objects live in buckets, so that's a container for a collection of objects. So it's not exactly the same as a directory on a typical file system because it's a flat namespace. There's no hierarchy or anything like that. But that's good for large-scale work because the metadata and I/O overhead for dealing with directory and all the POSIX semantics tend to be one of the bottlenecks in very large-scale and high-performance stuff. So that's one of the reasons that this S3 style is appealing. And each bucket lives in a particular cluster or site or region. With Amazon, that might be, one of the different physical regions throughout the globe. That also might be a particular cluster if you're running a private S3 service. And replication, which is the main topic here, is automatically propagating objects from a source bucket to a destination bucket. You might do this across different sites or within one cluster. And this is not the same as synchronization. If there's already stuff in the bucket when you turn on replication, that's not automatically transferred. And we don't have stuff happening in the destination bucket propagated back to the source. So it's more of just responding to new objects being put into the bucket. Or objects being deleted from the bucket. That can also be propagated to the destination. So there are a variety of reasons that somebody might want to use this multi-site replication. If you're going across different availability zones or multiple clusters, you can have redundant copies of the data that are automatically replicated if you want to have very high durability. If you have users in different physical locations, it might make sense to keep a copy of the data close to the users. You can minimize latency that way. Or if you're doing some, move the computation to the data stuff, you might want to be replicating data to different clusters where compute is happening. There are a number of different storage classes with different prices that S3 offers, or you might be doing a mixture of public and private cloud. So you might want to be automatically moving and shifting data around to these different storage providers. Sometimes there are legal requirements or policy where you need to store data in different locations, possibly with different protections, or just shuffling data in between different accounts. And you can also use this for setting up some interesting application logic. If you've got logs going to different buckets and you want to collect them into one, or you're doing some serverless event-based data flow type stuff. This can be very useful for generating an artifact and getting it copied somewhere else where it's going to be used later in a workflow or something like that. So the way that this looks in Amazon's S3 is that a user sets a policy on a given bucket. So on the right, I I have what one of those policies might look like. There's a role there that specifies, credentials and who's going to own things when we're replicating. You can use filters. Here there's a filter saying that any object name that starts with foo is going to be replicated. And you can also have multiple rules so that you can replicate objects to different destinations. So after you've placed one of these policies on a bucket, then the user uploads an object to that bucket, and if it matches one or more of the filters, then we are going to replicate that object. So the S3 server will put some metadata on there, a special field XAMZ replication status that shows up a lot in this talk, and it'll be marked as pending. But then the object put succeeds, the user gets an OK and continues with their work. And then after some time, that replication will happen in the background. So the object will show up in the destination bucket, should have all the same metadata as the source object. And that metadata field, the replication status, gets updated once replication completes. It'll either say completed or failed. And then replicas are also marked so that they can be identified. So there are a number of challenges in implementing this correctly. So these are the things that we need to tackle and make sure that we have a robust and reliable solution in CORTX. So one thing is we can't just be best effort or forget about some of these objects that need to be replicated. They might be a key part of correctness of applications. So we need to make sure that our replication system is reliable. We also need to make sure that it's asynchronous. I'll talk in a bit about why we can't just do simple synchronous replication. But we want to make sure that object put is efficient and doesn't bother the user with unpleasant effects if they're trying to use this replication feature. We need to be fault tolerant. This is a distributed systems world, so any component can and will fail. So we need to make sure that none of those failures will affect the replication and cause, undefined results or lost replication events. And that ties into reliability above. And we also need to make sure that our replication approach makes a faithful copy of the data. So we need the contents, the metadata. AWS supports, the S3 supports different version IDs. So we want all of that to be preserved when we're doing replication. So one simple approach might be just replicate synchronously. So when the user puts an object, that's step one. Then to A, we store it to our storage cluster. And then at the same time, we also put that object to these other replication targets. So those other little S3 clusters on the right. And then once all of that is done, step three, we go back and tell the user, OK. So an issue with this is the performance and the time to do that put now depends on all of those connections to these external sites. So we're dealing with the max of the latency and the time for doing that, which is not a desirable situation to be in. And a lot of times the storage link to between the S3 server and the storage layer, they're in the same cluster. There's a very fast connection, maybe like InfiniBand or something, whereas we might have slower connections to these other sites. So we don't want the critical path and the time limiting step in that link to be replicating to these other sites that might be over a slow connection. This also sets up sort of unbalanced use of bandwidth. So if we're replicating large objects and we have a lot of, like several different replication sites, we might be eating up all of the outgoing bandwidth doing this replication. So this is generally, there's a number of problems with this. So we don't want to do things synchronously. We want to be able to manage things in the background at our leisure to make better use of bandwidth and available site resources. So the simplest modification here is to just do background replication through the S3 server. So the only change here is after we store the object, then step three, we immediately return OK to the user. And then at some point in the future, we have a background thread or something else that does replication object puts to the different S3 servers. So this can solve the issue that the user sees terrible slowdowns when doing replication, but it is not great in terms of reliability and robustness. So the state of what needs to be replicated where is living in that S3 server. So if that crashes, then we might have undefined state or issues with the object being stuck in pending forever or something like that. So we'd like something where the replication state is stored elsewhere. And this also isn't great if we're trying to scale out, because that S3 server where the original put happened is the one who's doing these subsequent replications. So if you have an object that needs a large number of replication targets, you might be overloading that one server. So if we have, a load balancer that's routing requests to different S3 servers in our cluster, we don't want all that load to be concentrated on that one server responsible for that replication. We'd like to be able to distribute that load so that we can scale out better. So the next modification is we add a separate service that is doing the replication, and then this is just on the side communicating to the S3 servers. So we don't have that hotspot type effect on the original S3 server. The main issue here is we need to be very careful with correctness and consistency and not losing events, because the replication service is, of course, another thing that can crash. So if we have, some unpleasant situations where the replication server or the S3 server crashes in the middle of an operation, we don't want some of those updates to get lost and have objects stuck unreplicated and have an inconsistent state there. And the S3 service APIs don't really have a good way to look for unreplicated objects. So we wouldn't want to do, say, a linear search on a large bucket to see if we missed anything. That would be a performance problem there. So what we really need is something like a multi-producer, multi-consumer queue, where we can have these replication events that are occurring as S3 objects are being put, and then the replication service is able to handle those. We need to be, persistent with this queue to make sure that we don't lose any events. So that is the architecture that we are using for CORTX. So the key points here are that the notifications that an object has been put and replication is happening are handled lower down through the motor layer. So the idea here is that the storage system is the one who's aware of the state of all these objects, and it's aware of, when transactions finish and all that. So that's the best point to do these notifications so that we don't have, the S3 server crashing after it stores, but before it's able to send one of these notification events. And then we have a connection to the replication manager, which is done using Motor's FDMI interface, which I'll talk about later in the talk, which is a publish-subscribe mechanism for different events that happen in the system. And then again, we have the replicator that's doing the actual gets and puts, and that's just using normal S3 APIs to get the object from the local cluster and send it out to target destination clusters. So for the remainder of the talk, I'll be going into the different components that we have in CORTX that make up the solution. So I'm assuming if you're here for the Meet an Architect talk, you've probably seen something about Motor before, but just a bit of background. It's the main storage component in the CORTX stack. We do all sorts of clever things with multi-level erasure coding, horizontal scaling, all those great things for managing storage nodes. We have highly reliable storage for objects and a distributed key value store, which is very useful for metadata in this S3 setup. And we, of course, designed for extreme scale, advanced storage configurations like high-capacity hard drives, NVMe, all that sort of stuff. But this isn't a talk about Motor internals. So for the purposes of this talk, we'll just treat Motor as a service providing an object store and a key value store interface. So the CORTX S3 Server is the component that translates those S3 REST APIs, like get an object, list the contents of the bucket, and translates into Motor operations, which is talking to its key value store or updating object metadata and that sort of thing. So the S3 server is designed as stateless. And an advantage of that is that we can scale out to meet increasing load. So if we have a lot of activity, we can provision more S3 servers, and those can do parallel access to the motor cluster. The authentication and authorization is also a separate service. But one nice thing about the S3 API is that each request has to come with all authentication data. So it works very well with this sort of stateless horizontal scale out approach. And S3 Server is one of the components that we are actively developing. So we're always adding more API coverage and getting more and more improvements there. So the way that the S3 server in CORTX looks is shown here. The client makes an HTTP request for bucket contents or what have you. That'll go through a load balancer, which dispatches it to one of the S3 servers, and then those can scale out in or out as needed. There might be a check for authentication, authorization needed, so the S3 server can do that. And then once the request is okay, then it talks to the motor cluster to get the actual data or metadata and pass all that back to the user. Oh, and then in this drawing, I know I have a little hard drive here for the motor cluster, but that's of course a large number of hard drives and probably a large number of nodes. So that's an entire storage cluster there. That's not just one hard drive. So the way that this looks under the hood is we are storing metadata for these different components in Motor's key value store. So for each bucket, there's some metadata, like it includes the owner, ACLs, timestamps, basic stuff like that. And we also have pointers or references to other components, like the list of objects in the bucket, the pending uploads, that sort of thing. So the metadata includes links to those other components that are also stored in Motor. And if we set up replication on a bucket, that replication config that I showed a few slides back is also stored here in this bucket metadata. And of course, if we're doing remote clusters, we'll need some replication to remote clusters. We'll also need some credentials to access those. So those can be stored off to the side through the authentication manager. And then that role field is what we can use to look up which credentials we're going to use when we actually carry out the replication. And objects in our CORTX S3 server are done in a similar way. There's an index of all the objects that live in a particular bucket, and that just lists the metadata for each object. So we have basic stuff like the size, the MD5, the object name, and all that. That Motor OID field is a reference to the object stored in Motor that has the actual contents of the S3 object. And if we are doing replication, there's also that XAMZ replication status that gets added as well. And then we can have the state of the object stored there. So when we are doing replication, the basic steps, we first check if the bucket has a replication policy installed, and then we can also get the role that we're going to use for that replication. When the user puts the object, then we need to check if it matches one or more replication rules. So you can filter by the object name. You can put tags on the object and filter on those. So we need to do some checks to see if this particular object will be replicated. And then we might need to use that role information to get credentials if we're accessing a remote cluster. And then basically the S3 server just needs to apply a metadata field, which is that replication status, to the object metadata, and that's it. It's not responsible for notifications or doing actual replication or anything like that. It's a very small change to be able to replicate objects from the S3 server's perspective. So the component that does the notifications is FDMI, or File Data Manipulation Interface. So this is CORTX's novel publish-subscribe system for getting notifications of interesting events that are happening in a storage cluster. And it's set up so that you can connect multiple plugins listening for different kinds of events and get fine-grained notifications on individual I/O actions. So it's not just a bulk log or something like that. You can get active notifications of events. And it supports filtering so that you can restrict what you're interested in from the cluster, because presumably there'd be enough events to overwhelm pretty much any listener. So we want to make sure that we can filter that down to just the things that you're interested in. And there's a number of different uses for FDMI. We're using it here for a replication type thing. You could also use it for backup, switching between different storage tiers, interesting stuff with burst buffers or compression background stuff. Also useful for auditing or interesting indexing or searching that might be useful for managing this large amount of data that's hard to figure out what you want. And this can all happen automatically in the background, and supports plugins that are connected to Motor's core but are easy to modify and switch out. So you can have flexible adjustments to the functionality of Motor without having to rebuild the whole system. So the way that this might look, I have a little diagram with our Motor cluster here and two different FDMI applications plugged in. So first we have a put of an S3 object, and we have those different metadata fields, and we have replication set. So our FDMI event would notice that, and it wants to notify the replicator. So we have that FDMI notification going through and goes to the replicator, but we don't notify this other, this auditing application about this. And we might have, say, a security log or something else being stored in the Motor cluster. And that might trigger a different FDMI event that has some different filters, and that'll go to our audit service. So the idea is that you can plug in a number of these different applications and do all sorts of interesting things with what the cluster is doing with I/O operations. And it's designed as a very, very flexible interface. So the way that FDMI filters are set up, you can include them as part of the cluster configuration. So on the left, we have the YAML type cluster config. And here we're doing substring matching on bucket name, object name, and that replication header. So if we see an S3 object event coming through Motor, then it'll match this FDMI filter and notify the replicator. And on the right, we have sort of the low-level config that Motor uses internally. It has the same basic information there. It's sort of a bit harder to read because it's translated to concrete IDs, but you can see that we're setting up an endpoint where the applications can connect that IP address and port there to find new updates on the FDMI events. So an FDMI event itself looks something like this. There's an opcode. Here we have 231, so it's creating a new entry in the key value store. There's some extra info, like which node is the source, like which particular Motor node is the source of this, which can be useful if you're doing clever things like taking advantage of data locality and that sort of thing. And then we also have the key and value that were put into Motor's key value store. So here we have the object name and the value, which is just the whole object metadata. And this is where we can do the substring matching on these different metadata fields. So the idea is, from the S3 server perspective, we just have to put the object metadata into Motor, and then FDMI will pick up that object metadata and send the notification for us automatically. So FDMI has some very nice properties which align very well with the requirements that I gave earlier in the talk. Events are reliably delivered. The whole FDMI setup is tightly integrated with Motor's core, so there's persistent notifications. We make sure not to lose those notifications, and it's aware of transactions and all the distributed stuff that Motor is doing under the hood. So all the things are kept consistent. It is possible to get duplicated events, but for replication, that's not an issue because we can just check if we already replicated an object or if it's up to date, so that's no problem. FDMI lies outside the critical I/O path, so there's a separate RPC mechanism that applications can connect. The interface of FDMI is a publish-subscribe interface, so applications can listen on the particular filter that they registered for, And once they have finished handling that event, they explicitly release the event. So Motor persists those events until the FDMI application tells it, okay, I'm done handling that. And of course, Motor is designed for fault tolerance, and FDMI is the same. So if our FDMI application crashes, then those events will be queued and we'll deliver them once the service is back up and running again. So one little digression here is, why didn't we do all this in the S3 server? So Motor provides a number of primitives that we could use to implement, say, a queue here and do something similar, or we could use an existing pub sub system. So why is FDMI better than doing that? So a key point is that it's deeply integrated with Motor. So if we have transactional updates and all the complicated things that can happen, we don't need to worry about the implementation in one of the clients getting out of sync with what Motor knows about. And for some of the other uses, like moving compute to data or doing some local compression or something like that, you can take advantage of data placement that FDMI is aware of to make sure that you're doing operations on nodes where data is available. Another key advantage is that we didn't really have to make architectural modifications when we're using FDMI. So with the S3 server, it's not like we had to dig around in the event loop and add in a queue or something else. We just had to add one metadata field, and Motor would pick that up and do the rest via FDMI. So if you're writing your system from scratch, you might not care as much, but if you're working on connecting an existing system to Motor, then the fewer changes you have to make and the fewer architectural changes, the better. The capabilities that FDMI offers are very flexible and can be adapted to a number of common situations. And it abstracts away a lot of the tricky distributed systems problems that we don't want to have to worry about getting right in every client application. So as an example, another S3 feature is webhook notifications, where after an object is put in a bucket, you might want to have the server send an HTTP request to your own server to get a notification about that event happening. And that has a lot in common with what replication does. And we'd rather not have to redo all of this, setting up a queue and making sure that we don't lose events and reliable delivery and all that in each time we add one of these features. If we can handle that at the Motor layer and have one rock solid implementation, that's better. And the last component to look at is the Multisite Replicator, which is the piece that actually carries out the replication. It listens for those FDMI events and gets the object that is now stored in the local S3 cluster and sends it out to the remote cluster. We have the best support for replicating to other CORTX clusters, but you can also point it at AWS or MinIO or one of the other implementations and replicate objects there. And again, we're designing for fault tolerance and scalability, so we need to be able to scale out the number of replicators to meet load or take advantage of bandwidth. And we need to make sure that we are fault tolerant so that if one of the replicators dies, then we can recover and not lose anything. So the way the multi-site replicator is set up, we have the Motor cluster here, delivers an FDMI event to the replication manager. So the manager's job is just to keep track of who's doing what and dispatch tasks to the individual replicators. It doesn't do any actual transfer IO type activity. So it'll choose one of the replicators and send a replication task there, which would be, the source bucket, the object, any credentials it needs, that sort of thing. And then that replicator instance would be the one who's actually connecting to one S3 cluster, which would be the local one, and putting the object in the destination. And as I mentioned, we can scale those number of replicators. And the events here can be persisted until the replication completes, to make sure that we don't lose anything. So the basic process here is fairly straightforward, similar to what I think I covered a lot of it in the last slide. When an FDMI event comes in that indicates that we need to do some replication, then we'll need to validate the metadata, want to make sure that we don't have any accidental replications happening if there's an edge case, like somebody uses one of our special substrings that just is part of the object name or something. We'll get any destination information, remote cluster credentials, and then we will send that replication event to one of the instances. And then once that's scheduled, it'll start executing. We'll hear back from the replicator, and then once everything's done, then we update the replication status to either completed or failed on the source object. And like I said, the replicator instance is the one that's doing the actual transfer. So it gets an object, validates to make sure that we're sending the right object, we haven't replicated it already, and then it does a put to the destination object. So when we're doing replication this way between two different CORTX clusters, everything is going to work beautifully. If we are replicating to another provider, there are some issues that can show up. So one is the metadata on the source and destination objects won't match. The creation time, for example, would be when the replication happened, not when the source object was created. And there's no way to change this using normal S3 APIs. So we can work around that with CORTX, but if we're dealing with another provider, then we can't really change that. And version IDs are another area where this shows up. The S3 server is the one choosing version IDs. So if we are sending to a non-CORTX S3 server, then they'll choose whatever version ID they want. So we can't make that match. And of course, to make the metadata updates for the changing pending to completed or whatever, we of course need the source to be a CORTX cluster, because that is also not standard API for S3. So the way under the hood that CORTX does some of these metadata type operations to make sure that everything lines up correctly, we have some internal management APIs for directly modifying metadata. So that's how we can flip from pending to completed. But those aren't something the user should be aware of. And we're also setting up some special headers that we can put on objects so that you can specify a version ID or create time or other metadata that you want. And the S3 server will be aware that for normal users, we don't pay attention to that. But if we have a connection from a special replicator account, then we need to be updating those to make sure that everything works correctly. So this has been a quick introduction to the multi-site replication in CORTX, and a quick tour of the different components that we're developing to make that work. If there are any questions or any other discussion, I'm happy to take those.
Everyone should be able to themselves or leave a comment in the chat if they have a question.
I have a question about that. How do we clean up the notification queue? Maybe I missed this bit. So you told that the replication agent, as soon as replication is complete, it somehow will clean it up. Can you elaborate a little bit?
Yeah, so I should preface this by saying there's active development in that area. So at the moment, there are some other things, like we have separate queues in place for avoiding working around some things that are currently under development. But in the idealized case, the finished case, once everything's set up and going, the FDMI interface will persist events that have been created. So a subscriber can get one of the events, but that doesn't clear the event. They'll need to explicitly release that event once they're done processing it.
Yes, and here is another question. What if there are several subscribers, and how they coordinate? If one of them deletes the event, how the other one can lose the event? So how do we do this?
Yeah, so that's why we have that extra piece, the replication manager, in there. If we just had a bunch of independent replicator instances, then they would be stepping on each other's toes all the time. So we have the replication manager, which might end up being, a whole set of different components, say in a Kubernetes cluster. and it might have its own persistent storage internally to make sure that we don't have, inconsistency there.
Hey, Tim, there's a couple of questions in the chat. Do you see those?
Oh no, I should stop sharing my screen. I can't see the chat.
I can read them too. Ongji asks, how do we receive FDMI events?
Internal to motor, each of the different storage nodes, each of the different motor nodes that has some local storage attached has a set of different things it's looking for the FDMI events. And as part of the communication between nodes, those will be sending updates. But for the from the perspective of a user of the system, the FDMI events have an RPC type interface, so there'll be a particular address and port that they can connect to, and then they'll be able to get the recent events, get a particular event, send that release, so they can send RPC messages back and forth between the motor cluster. So there's sort of a loose coupling between the FDMI applications and the motor cluster.
Awesome, thanks. Pete Brown, thank you for chiming in. Pointed out that there is a sample FDMI app in the repo, and so suggesting to look at that. I will point out also, Pete, we are working to improve that. I think that sample app is pretty good, but we have an intern that did some great work for us this summer, Liana Valdez, and she made a better FDMI sample app. So she's working to improve that documentation. So yeah, please keep paying attention to that, and that should be going out in a newsletter soon that we've improved that. Also, some questions, Tim, from Zuhair. So Zuhair is asking, what about fault tolerance? Can you discuss a little bit about fault tolerance in the replication manager and the replicators?
Yeah. Like I mentioned, we're in distributed systems world, so we have to make sure that any piece can fail, be restarted, and safely resume. So for the replicators themselves, those are designed to be sort of stateless in the same way like the S3 server was kind of stateless. They just are aware of a particular replication job that they're doing at the moment. So if one of those dies in the middle of replication, then we'll find, the remote cluster didn't get, the object put completed or what have you. And then we'll never get a success, complete notification to the replication manager. So we'll have to notice that that replication event, timed out or didn't work. So then we'll schedule that event to another replicator instance and then try it again. If the replication manager dies, then it's a little bit trickier. If we have some, local persistent state that the replication manager can use by itself, then we might be able to recover more of what the in-progress states were and resume immediately without dropping anything. But if we go to worst case scenario where we don't have state available for what the replication manager was doing, we could try to fall back to what the FDMI events are still available through motor. And then if we redo a replication, it's not going to affect the correctness because we'll just be copying the same version of the object to the destination cluster again. So it's wasted effort, but it's not going to be incorrect. So even if worst case scenario, we end up redoing some of those events, we'll still be okay.
That's great, thanks. And looks like one last question so far is a single replicator responsible for replicating to all targets, or is it one replicator per target? And this reminds me, Tim, that this question also feels a bit similar to the demo that Hua did, showing that you can have two different triggers, but I think that's different than multiple replicators. But maybe you could discuss the multiplicity in both aspects of the system.
Yeah. So like Hua's demo that you mentioned would sort of line up with the one slide I had a while back where you might have two different applications, say our replicator and like an audit system or a backup system. You can have different FDMI applications that can listen to a different set of events. They can have their own filters. and then you can plug in, and we have plans to be able to add and remove and dynamically configure these applications while the system is running. So there's a lot of flexibility in terms of different components that you might want to stand up for listening to different kinds of events. And then as far as the replicator itself, I don't know off the top of my head if it's set up to do one replicator for each target, or one replicator handling the entire replication event. I can look up and chat with some people and get back to you about that. Either way would be perfectly feasible.
I believe it's set up that it's a single replicator for all target. Well, it's a single queue for all targets, or it's a single queuing system for all targets, and it's a single replicator pool of threads pulling from that queuing system is my understanding. But as you say, it could have been configured in a different way.
Yeah.
And then Ongji asks, and I'm glad that Andre is on the call, because he might be interested in this and might actually be able to answer better than you, Tim. Ongji asks, is there a future plan for other languages binding to FDMI interface? For example, Golang.
Yeah, I mean, I don't think there would be any technical impediment to that. I think it's just a basic RPC interface, so it would be definitely possible to connect other languages. I don't know if there is any active plan or development. So yeah, if Andre wants to.
I don't think that on the motor side or on the CORTX side, right? There's sort of like a client. There's a client for FDMI effectively, and that client the client needs to subscribe using the existing motor interface. So that's a good question. Could we create like a Golang interface to subscribe and to set it up? But ignoring that, once it's set up, as you say, you're just an RPC client. So if Golang supports RPC, then yeah, I think because we have both Python, we've demonstrated, I believe, both Python and C FDMI applications. So anything that can receive RPC can be an FDMI application, an FDMI client. Is that correct?
Yeah, I think so. And one other thing to note about our sample FDMI apps. So the FDMI app that Liana was working on is nice because it can take in those events and just emit some JSON that you could then pipe into another language. So I think for the one, it was just sort of being piped into another program. So if you have a language that supports JSON, which is pretty much everybody, then you could use some of our existing, example FDMI apps to get running quickly, just processing these events that are being translated for you.
That's a great point. Thanks, Tim. So I think Rachel was messaging me that she was having some issues with echoing in her audio. So if there's no more questions, I think we can give people a couple of minutes and the other day back. But hey, Tim, that was a great presentation. So thank you so much.
Yeah, thank you.
So thanks again, everyone, for attending our monthly Meet an Architect session. Really excited to have you, really excited to have the opportunity to share with you the cool stuff that we're doing and get the feedback from the audience. It's really great. If you haven't yet, please join us in GitHub. Please join our newsletter. If you want a sticker, hey, we're happy to ship out stickers. So thank you all so much. Have a great day, everybody. I hope everybody stays safe out there.